observable states when you are in certain state. Say sunny is my S1 state, rainy is S2 state, and say cold is S3. So when I am in actually sunny state, when my system is at S1 state, what it will emit as the observable variable. So we have three observables, that is sweater, umbrella and short. So the chances are given in this table. So when you are in the state S1, wearing sweater chance is 0.1, that is 10%. Carrying umbrella is 0.4 and wearing shorts is 0.5. So this is total equal to 1 again. When there is a rainy day, you have another probability. When it is rainy, wearing sweater is 0.15, carrying umbrella is zero point 0.8 and so on. So this is also a table with row equal to 1. Row sum is 1. And this is called as emission matrix. Why it is called as emission? Because say this is my S1, S2 and S3 transitions. So I am doing these transitions. So whenever I am at S1, I can emit different symbols. Whenever I am at S2, I will emit different symbols, that is 3 symbols suppose. And here we have the chances of emitting these symbols. So I can call suppose sweater as V1 and umbrella as V2 and the shorts as V3. Then these are the symbols that are emitted by this machine. Okay, so at each state you have a different probability of emitting these symbols. Okay, so this is given to you. So this is somehow known to us and this is given to you. Then you have one more quantity with you, that is the initial status of your machine. So when you start your machine, what was the initial status? So as all weather is suppose equally likely, that is you can have sunny day, cold day or rainy day, chances are equal, then we can have this initial guess. Remember sum of this is also 1. Now if the question is what is joint probability that this sequence of days and this sequence of symbols emitted by the system. So hidden states are sunny, sunny, rainy, cold, and accordingly the emitted symbols are umbrella, short, umbrella, sweater. So these are visible, that we can observe this, but these are not visible. But somehow suppose I know this, then what is the joint probability that sunny, sunny, rainy, cold, and along with that umbrella, short, umbrella, sweater? What is the joint probability? So that means what is the hidden state and observable state? What is their joint probability? So you can use your table and then you can easily find out what is this. So we have this pair indicating the first sunny day. Since the first day we don't have any prior, so there is no conditional bar given here. So it's coming from initial state. So the table is saying that it is 0.33. So that we are taking. Then when you see the first day, you observe that the person is coming with umbrella. Okay, so this is day 1 and it is coming with the umbrella. The hidden state is actually sunny. So what you see, probability of sunny into this probability of umbrella given sunny. So you can go to the table and check that values, and you can keep on writing all the probabilities one by one. Just take the multiplication, that will give you the answer for probability of hidden states and observable states. This is, remember, joint probability. I am saying and. Okay. Now that was the simple introduction. Now there are 3 problems that HMM can handle. The first one is called as evaluation problem. The second one is called as decoding problem. And third one is the most important, is learning problem. The first one, what tells you what is the probability that given a model theta. When you say you are being given the model theta, that means we are providing you matrix A, matrix B and initial state pi. So this has been given to you. Then there is a sequence of observations. Say O is a set of observations, say up to suppose OT. So these are observations that we have observed. Now I want to answer the question, what is the chance that these observations, are produced by given model? Say you have many models with you for different purposes and you have seen this sequence O. Now out of these, suppose 4, I want to know who has produced this sequence. Okay, who has produced this set of symbols? Say for example, we are dealing a problem of, say, speaker recognition, and these are, say, models of each speaker, and then we fed some signal, a sound signal, and we want to identify who has spoken this. So this input will go to all models, and these models, these are all HMM models, they will give you the probability of, say, uttering these input by this person 1, person 2, person 3 or person 4. So then you can decide which probability is higher. So that person might have spoken these words. Okay, so in the same way we call, instead of words here, symbols. Okay, so these are observable symbols. These are observable symbols. Then who has produced this? Which model has produced this? That we want to find out. So that is called as evaluation problem. The second problem is called as decoding problem. Given a sequence of visible states, the decoding problem is to find the most probable sequence of hidden states. Now see, there are 2 things, as I said. Say this is my observation. Say I have observed this sequence of events from outside the system. I don't know what is going on inside. Suppose there are 4 states or 5 states. Machine is at what state? This is not known to me, but I can observe these states from outside. So predicting when the machine emitted symbol 1, what was the state at that time? Then machine emitted symbol 2, what was the state at that time? So we want to find out like this. Given this set of symbols which are observed, what is the best possible sequence of hidden state? Or what is the most probable sequence of hidden state? So there are many possible combinations of hidden states. Suppose there are two hidden states, say S1 and S2, then you can see that first one is S1, then second one is also S1. Okay, third one is also S1, fourth one is also S1, but observables are this. Okay, so when you have when you observe O1, O2, O3, O4 symbols, you may have this sequence, or you may have S1, say S2, or let us take S1, S1, then S2. So you can have such 16 possible combinations just with these two status. Now if I add one more, then you can imagine. So this will be growing exponentially when status are increasing. So decoding problem is to find out what is the most likely sequence of hidden state when I observe something. Okay, so that is called as decoding. Now last one is learning, that means finding out A, B, this transition matrices from given data. So this is learning problem, that means of training of HMM. Now we will deal with evaluation problem. Find the probability that a given model theta has produced a sequence of observations O1, O2 up to OT. So length of observation is capital T. Now earlier we have calculated joint probability, that is hidden state and observable state. But since transition of hidden states are unknown, this probability calculation is not straightforward. So when you just see umbrella, short, umbrella and sweater, what was the day here? This is not seen by this person. Okay, the person can see only this thing, umbrella, short, umbrella, sweater, but what was the actual day outside is not visible. So that can be any combination. You can see, so I can see umbrella, short, umbrella, and the actual day outside may be sunny, rainy, sunny, cold, or it can be cold, sunny, rainy, sunny. So any combination you can see. I can have say sunny, sunny, rainy, say cold and rainy. So like this I can have any sort of combination, but I have observed only this thing. Then question is how to find out whether the given set of observations are produced by this given HMM. Whether this sequence is produced by our model with A, B and Y. Now let us say the probability of obtaining some observations O1, O2 up to OT given this model theta. So given this theta, what is chance that I can see these observations? So that is the first problem. So there are three problems we are now dealing with. First problem, that is evaluation problem. So model is ready made. We have this theta with A, B and pi. So this is ready made to us, and we are provided the set O with O1, O2 up to OT as the observations, and the question is whether this sequence is produced by the particular model. Now we can see that there are many possible combinations of these states. You can have different possible combinations of the hidden states, and still you can produce the same sequence. So remember, so your states can be anything, but you can produce same observables. So what we do here, is we add all such probabilities. Now try to understand this equation. What this equation is the probability of observing a set of observables, that is O, sequence O, given this model theta. This is equal to some summation I equal to 1 to NST. So where NS stands for number of states. How many hidden states you have? Say there are 3 hidden states in our earlier problem. I know there are 3 types of days: sunny day, then cold day and rainy day. So such number of states, how many are there? So that is NS. Now NS to the power T. So this is the number of possible combinations of hidden states. Number of possible combinations, or I should say permutations of hidden states. So that is the maximum possible. Now this is the sum over the probability of observing O, or probability of obtaining observations O given a state Si. Given a state Si, what is chance that I will see the given observations multiplied by the probability of obtaining that states itself, hidden states itself. Okay, so where Si is ith state sequence. So I can see here S1 is one sequence, S2 is another sequence, and so on. So there are how many sequences? In total, there are ns to the power t number of sequences. Okay, so for each sequence, what is chance that it will see this observation? So given a sequence, suppose I give you a sequence S1, S2, S5, then S3, like this. So this is one sequence. Then what is chance that I will observe O2, say O3, O4, maybe O1. So these are my observations. What is chance that this sequence will do this? Multiplied by chance of obtaining this hidden state. So if I sum over all such states, sequences, then I can get the total probability of obtaining this O sequence. Now see why I am not caring about what is the hidden state transition. When I do this sum, that means I am not caring who has produced or which sequence has produced this observation. I am interested in just the observation that this machine can produce. So what we can do is we can take all possible combinations of hidden states and ask the probability that sequence will produce this set of observations. Okay, so you can imagine something like this. Say this is my one sequence, this is another sequence, this is third sequence, and so on. How many such sequence I can generate out of the ns given? Say ns is the total number of hidden states. Then say 1 to ns to the power t, since I am generating a sequence of length t. So I have this many sequences with me. I will take one sequence and find out what is chance that this set of observables, say O1, some random observations I can write, O3, O5 and so on. What is chance that this is sequence has produced this? Suppose I get some number 0.01, then I take second sequence and then I just find out what is chance that this set of observation is produced by this sequence set number 2. Then suppose I get 0.1 and then I keep on doing till end. So everybody will give certain chance of producing this set of observations. Now final probability that this model will produce this set of observation is just add all this. Okay, so adding all this is nothing but this equation. Okay, I hope you have understood this. And then the next part is how to solve this. Now where this first term is nothing but the product of the probabilities given the state. Suppose sequence number 1 is going, in that I have the first state. Okay, so probability of obtaining some symbol at time t, small t equal to 1, there is some symbol, say at time t, I have seen some O1 symbol. So probability of this into when time changed, so I will see some observation 2 given sequence number 1 and then the state number 2. So like that I will keep on doing till I go to the last observation. And this is, remember, is done for sequence number 1. Okay, so this is done for sequence number 1. Similarly, we will change I equal to 2 and then find out for second sequence. And this will be a very huge calculation. You can then think of what is the complexity of this thing. So I will show you what is complexity. So this equation you will substitute here. Now we will use the Markov chain property of first order to find out this second quantity. Now what is that? That is nothing but the transition probability. So this probability of obtaining Si is equal to product of small t equal to 1 to capital T, the probability from, that is transition from previous state to next state. So Si t, suppose I put t equal to 1, so this is probability of the given sequence Si t equal to 1 given the initial state or the first step is with t equal to 0. So this will be multiplied by the probability of Si, the sequence, ith sequence, second time step given Si and first time step. So like that this will keep on, you will keep on multiplying till you reach the last time step. Okay, so this product will give you the second term, this one. So when you substitute these two things in your first equation, you will get this final equation. So this final equation, if you then see carefully, after substituting those two things, you can get this final equation. Now they see the complexity, the computational complexity of above equation is ns to the power t into t. For example, if ns, that is number of states, are suppose 10 and the sequence length is 20, then the number of computations of above equation, it looks very small equation, but the computations are of the order 10 to the power 21. It's a huge computation with only 10 states and length is 20. Now, to reduce the complexity, we have to deal with this equation differently, because to calculate this thing, there are many repetitions, or the products are repeated quite frequently. We can avoid those things. So the algorithm that is used to do this is called as forward algorithm. So we can calculate the probability of, that is observing this sequence recursively, since each term involves only this observable, then state and previous state. So current state, previous state and observation symbol. So only three things are required. So then we can reduce the complexity. Now to do this, what we do, suppose we have this n states and this is time step 0, 1, 2, 3 and so on up to t. So I write suppose all states with me here. Okay, and let us say this is my initial state, and then I proceed up to t states. say from here I can go to S1, I can go to S2, I can go to S3, I can go to Sn. I can go anywhere from S3. S3 is the beginning, so this is fixed. This is known to me as at time step 0. There will be transition from T0 at T0 from S3 to all other states that is possible or allowed. Now we are going to calculate a term called as alpha for each of this state for each time step. Okay, so as I progress in forward direction, for each time step we are going to calculate alpha. So alpha 1 here is for state number 1, time step number 1. So alpha 1 here is for step number step number 2 and state number 1. So this alpha n2 stands for state n and time step 2. Now we are calculating this alpha based on the previous time step. Now what exactly is this alpha? We will see. So alpha is the probability that we see these symbols O1, O2, O3 up to OT and state Si. Now see, I am standing at some time step T. Okay, I am standing at some time step T. Let us say I am standing at say time step T equal to 3. Then I stands for the ith state. So this alpha is probability that I observe some symbol O1, I observe symbol O2 and a state Si. Suppose this is 1, then this will be 1. So suppose there are 3 such states with me. So alpha 3, 2, then alpha 3, 3. So I have 3 probabilities with me. So what it stands for? At time step t equal to 3, what is probability that I stand at state S3 and I have seen these symbols O1, O2. So this is the calculation of alpha. So this is looking maybe complicated, but it's very straightforward. If I directly jump to the diagram, suppose this is some transition diagram and these are some A matrices and B, this is given to you, and then suppose I do this transition calculation. So initially my state is S1. Now see carefully how we do it. So say for alpha 0 at time step 0, my state is fixed to S1, so the other alphas are 0. Okay. Now only alpha which exists is the initial state with 1. Now this alpha will be multiplied, say alpha 0 will be multiplied, that is the probability at state S1, I know it is 1 because this is the beginning, multiplied by this 0.2 and 0. So what is this? So you go to the table. I am moving from, or I am actually calculating the transition from S1 to S0. So state is suppose S0, then what is chance that I will be there? Then this is probability from S1 to S2. This is the probability from S1 to S2, and this is from S1 to S3. Okay. Now when I go to this transition from 1 to 0, so 1 to 0, state 0. So 1 to 0 is 0.2 here. So I'm writing here 0.2 multiplied by the probability of observing a symbol. So what symbol I have seen here? I have seen symbol O0. So just go to this O0. So what is chance that I will see O0 when I stand at S0? So this is actually 0. Okay, so this probability that you are in state S0 and you watch the symbol O1 is 0. So that's why we are multiplying it with 0. Then let us look at one more thing. Say, let us see this calculation. So from S1 I am going to S1. So from S1 I am going to S1. The probability is 0.3. And when I stand at S1, I am emitting symbol O1. So I am standing at S1 and I am emitting symbol S1. So probability is 0.3. So alpha 0 into 0.3 into 0.3, this will be alpha 1, 1 here. Okay, so what will be alpha 1, 0? This will be 0 because the product is 0. So like that, we keep on calculating alpha here. Now when I go to next step, I will be using this previous alphas to calculate next alpha for this node. So this will be alpha 2, alpha 2, alpha 2, alpha 2. So alpha 2 for state 0, alpha 2 for state 1, alpha 2 for state 2, alpha 2 for state 3. Then we will calculate alpha for 3 for state 0, alpha 3 for state 1, alpha 3 for state 2, and so on. So we will reach at this last position and then we will sum all the probabilities which are appearing here. So you will find that this sum calculated here is nothing but probability of O. So we will not go into derivation of this. We will just try to see what exactly is going on. So this is called as forward algorithm. That means you will calculate some alpha for each step and that will be used in the next step. So that's why these calculations are reducing drastically. So the calculation, if you see, that were earlier were 2 to the power 2 into 10 to the power 21. Now with this type of alpha calculation, they will go of the order 10 to the power say 3 for the same problem. Instead of 10 to the power 21, we have now 10 to the power 3. So we have huge reduction in your calculation. Now when you go to the decoding problem, what we have to do is, we have already seen calculation of alpha. Now what we want, what is the likely state that machine has traveled to generate the symbol O1, O2, O1, O3, O2, O0. So that we want to find out. So we have different values of alpha here. So what we do is, after calculation of this alpha values, we choose a path of max alpha. So whichever alpha is maximum, that we are choosing, that state we are choosing. So S1 for time step 0 produces maximum value of alpha, that is 1 here. Then when I go to time step 1, again S1 is producing the largest, S3 is producing largest value. So this transition from T0 to T1 is from S1 to S3. Next alpha maximum is occurring at S2 here. So at time step 2, the machine will go to the next step here, and at time step 3, the machine will transit to S1. And finally, for time step 4, machine will go to O0. Now this is a typical example in this case, that O0 state, this O0 state is called as absorbing step. Now if you see this diagram, you can come from S1 to S0, you can come from S2 to S0, you can travel from S3 to S0, but you cannot travel from S0 anywhere else. So once you land to S0, your transition is from S0 to S0 itself. Since you cannot move, this is called as absorbing state. Okay, so what decoding means, you will calculate all alphas and you choose a path of max alpha for each time step. So that way we can do, and I think I should stop, and I will stop here the syllabus. If you have any doubt, you can put a chat in WhatsApp, and then if required, we will discuss in tomorrow's class. So thank you very much.